Okay, let's solve this LeetCode problem, shortest distance after road addition queries 1. We're given an integer n and a 2D integer array queries. It says that there are n cities numbered from 0 to n minus 1. And basically, this cities constitutes a graph in a row, like this one. From 0 to 1, 1 to 2, 2 to 3, and 3 to 4. We don't have yet this. Initially, the graph is in this form, 0 to 1, 1 to 2, and 2 to 3, and 3 to 4. This is a graph, and the edges are directed from one side to the one vertex to the other vertex. And we're given queries. Each query asks us to add a new edge to the graph. And after that, it requires us to find the length of the shortest distance from CD0 to CDn minus 1. And we have to do this for each query. So we add 2, 4 to this graph. Now, currently, the distance from 0 to 4, and then we have to answer what is the distance from 0 to 4. We go from 1, so then we go to 2, and from 2 to 4. This is a distance of 3. We follow 3 edges to reach from 0 to 4. And then we add 0 and 2. And by the way, after adding the edge with the previous query, we don't remove it. So we just add the new edge to the current graph. So we have 2, 4. We have currently this graph, and then we add an edge between 0 and 2. And after we add 0 and 2, and then we answer the same question: what is the length of the shortest distance from 0 to 4? It is we follow this edge from 0 to 2, and then from 2 to 4. That is a length of 2. And then we add a new edge from 0 to 4. And then we add from 0 to 4. Then the distance, we can only, in just one edge, we can reach from 0 to 4. Now, let's see how we can solve this problem. In order to solve this problem, you need to know a graph traversal algorithm. It is called BFS for short, or Breadth-First-Seach. In Breadth-First-Seach, we start at a node, and then we ask what are the vertices that are one edge away from the current road. What are these vertices that we can reach by following one edge from the current node? These vertices are the ones that are adjacent to the current node. You can see by following one edge, we can reach 3. So the distance from 0 to 3, the distance is defined as the number of edges on the path. So from 0 to 3, we have only one distance. So the distance to 3 is 1. And another adjacent element is the vertex is 2. So the distance to 2 is 1. And also the distance to 1 is also 1. Now, these 3 vertices, now the distance to 0 is 0 because that is the starting point. So these 3 vertices constitutes the level 1. So basically, by going one edge deeper to the graph, we can reach that from 0, we can reach these vertices, 1, 2, and 3. Now, let's do the same thing we did to the vertex 0. Now, let's grab each of these vertices and ask the same question. Now, let's go and do this. Now, let's say we're dealing with 3. What are the vertices that we can reach in one edge, that are one edge away from 3? So there is 0, but 0 has already been visited and its distance 0. And if we go back here, its distance is, if we go back here, since we've come to 3 from 0 to 3, and if we go back to 0, its distance is going to be 2. So we go to 3 and then go back to 0. But it's already 0, so we don't have to do this. Basically, we do not revisit the vertices that have been visited. So how do we know a vertex is visited? If its distance has been defined, then it has been visited. So from 3, we have another one, 2. This is the same as 0. It has been visited, so we don't do anything. Then we have 4. For 4, we have not defined the distance. So 4 is 1 away from 3. So that is one edge. and 3 is 1 away from 0. So the 4 is 2 away from 0. So we add the distance on top of it. So it's 4. Now we grab 2 here. So from 2 we can go to 0, we can go to 3, we can go to 4. All of 3 have been visited. We have defined the distances from this node because we have 0, 3, 2 and their distances. So we don't do anything. There are no other vertices that have not been visited from 2. So we just skip this one. And then we have 1. From 1 we can only follow one edge and reach 0, and for which we have defined the distance. So we're done with this level. So we deal with this level. So now we have the next level. This level has only 4. So in this level, we have all the nodes, all the vertices that are 2 edge away from 0. And we do the same to this vertex as well. We ask what are the edge that can be reached from 4 by following one edge. So let's do that for 4. So we grab 4. We have only 6 here. As I said, we don't revisit 3 and we don't revisit 2 because we have already done this. So we visit 6. The 6 is 1 away from 4. So 4 is 2 away from 0. So 6 is 3 away from 0. So we write the distance on top of it. Now we also follow this. We reach 5. 5. We haven't visited 5. So the 5 is 1 away from 4. And 4 is 2 away from 0. 2 plus 1. So 5 is 3 away from 0. Now we have 6 and 5 in our new level. And we're done with all the vertices in our previous level. In our previous level, we only had 4. So now we have 6 and 5. These are the level 3. This is the level 3, and these vertices are 3 away from the starting point 0. Now we do the same to these vertices. Each one of vertices in the current level. After we process all the vertices in a level, then we move to the next level. Now let's do the same for these vertices as well. So we have 6 here. From 6, there is only one vertex we can reach. It's 4, but we have visited 4, so we don't do anything. And then we move to 5. From 5, we can reach to 4, but 4 has already been visited. And we can reach to 7, so we can reach 7. So 7 is 1 away from 5, and 5 is 3 away from 0. So 7 is 4 away from 0. Now we're done with the whole graph. So this 7 is in level 4. It's 4 away from 0. So now we have for every edge, for every vertex, we have figured out the distances from the starting point. So the task is solved for an unweighted graph. And if we're asked to find the shortest distance from a starting point to every other node in the graph, then we can use BFS, Breadth-First-Seach. Now, if we're asked what is the shortest distance from 0 to 2, then we have the answer. So for our current problem, we need this BFS. We need this concept because every time they asked us to find the distance from 0 to n-1, that these are given the vertices, and the graph from 0 to 1 to 2 and up to n, and they add a new edge every time when we process a query. Then after we add this new edge, we will run the BFS on the new graph. And then this is going to be pretty much the solution. Just to understand the concept better, let's apply this to the example 1. So initially, the graph is like this. We have cities, we have 5 cities. They're connected by a directed edge. It is always initially of this form. You're given this graph. And you have from 0 to 1, you have a directed edge. And it doesn't really matter if we have directed edge or undirected edge, as long as the graph is unweighted, or we do not have weights, different weights for each vertex, each edge, then we can apply BFS for shortest path. So then we have given some queries. This query tells us, okay, add a new edge from 2 to 4. So this is going to be the result after we applied this query. Then we have this graph now. Now then we run BFS on this graph. So what we said, the BFS will not only find the distance from 0 to 4, it will also find the shortest distance from to every other vertex. If we run BFS on this graph, it will find, okay, the shortest distance to 0 to 0 is just 0. Here it's going to be 1, here it's going to be 2, and from 2 we can explore 3 and we can explore 4. And so the distance to 3 is 3 and distance to 4 is also 4, because from 2 the nodes that are 1 away is 3 and 4 by following this edge. So 2 is 2 away from 0, and this 3 and 4 is going to be 3 away from 0. After we apply the query 1, basically adding the edge from 2 to 0, the answer for this query is going to be 3. So distance from 0 to 4 is 3. We just follow 3 edges. And then we add 0, 2. After we add this edge, now if we start at 0, what are the vertices that we can reach? It's 1 and it is 2. So the distance to 1 is 1, and distance to 2 is as well 1. And then from these two new vertices in level 1, basically the nodes that are 1 away from 0, then we explore other vertices. From 1 we can go to 2. We have already defined the distance for 2, and we can go nowhere else. And then from 2 we can go to 4 and 3. So the distance to 3 is 2, and distance to 4 is also 2. And from 3 we can go to 4, but we don't do that. We have already visited 4. So the distance from 0 to 4 is 2. We follow this edge to 2, and from 2, 4. So the answer for this query is 2. And right at the end we add a new edge from 0 to 4. So let me just go back up, and let me add this back. We have this edges. The answer for this is 3 and 2. Now after we add 0 to 4, from 0 we can explore 1. So the distance here is going to be 1. We can explore 2. The distance is 2. And we can also go to 4. So sorry, distance is 1, and we can also go to 4. The distance is 1. From 1 we can go to 2. We have already done that. We have the distance. From 2 we can go to 4. We have already done that. And we can also go to 3. So the distance to 3 is 2. And we're done. So the distance to 4 from 0 to 4 is 1. So that is basically the application of BFS. And every time we add new edge, and for the new graph, we run the BFS. We have at most 500. So we know that the time complexity of BFS is V plus E. So it's linear in the number of vertices and the edges. So if we have initially the graph has at most 500 vertices, and every time we add a new vertex when we apply a query, when we process a query, and we will have at most 500 queries, and this adds at most 500 new edges. So in total we roughly end up with n squared algorithm, which for given n, initially it's 500, this is pretty much fast. So this is all for this problem. Now let's see the code. Okay, let me explain this part first. First we create our graph. Initially our graph is like a linked list, and we create an adjacency list for the graph. An adjacency list, when we create an adjacency list for a graph, for every node we store the edges that are adjacent to it. For the node I, for the vertex I sometimes use node and sometimes use vertex. So the vertex I, we have only one vertex that is adjacent to it. It's I plus 1. Then we have the answer for every query. Then in order to answer this query, we first add a new edge to the graph. So basically we add an edge from the query for query 0 to query 1, query I0 to query I1. And then we call the BFS. The BFS will return the answer for us. It will tell us what is the distance from 0 to n-1. And then we put it in the answer array. So now let's look at the BFS. So in BFS, we have the distance array. You can have this other way around, but I do it this way. It does not really matter. So we have the distance array. The distance will tell you the distance from the starting point to every other vertex. So in our case, the starting point is 0. So basically this v is the starting point. And we have the queue. This queue will help us to store the current vertices that we have not processed. So basically, if we start at a node 0, just like we did before, then we explore some adjacent vertices. And if we haven't explored them, then we add this vertices to the queue so that we can process them later. So that is basically why we use queue. So as you might know, the queue, when we add to the queue, we add to the back of the queue and we grab from the front of the queue. So this prioritizes the elements in the front of the queue. Basically this means the values in front of the queue might be the ones that we have processed in the previous level, that we have explored in the previous level. So that's why we use queue here. And the distance to 0, the starting vertex is 0, that's where we start. And then we explore, then we do this while loop. As long as we have some element in the queue, some vertex in the queue, we grab this vertex, the front of the queue, and we pop it up, and we explore we visit all of its adjacent vertices. These are one away from the current vertex v, and this u is an adjacent vertex to v. So if we have not defined it, basically then the distance is -1. So then we say distance to u is equal to the distance to v plus 1. So that's the distance to v from the starting point plus 1. We follow one edge to reach u from v. And then we add this to the queue to process it later. Then after that, at the end, we return the distance n-1. This is basically the distance from 0 to n-1. So this is the BFS. And as we said, we call this BFS for every query. And this is actually pretty fast. So even if there is another solution for this problem, the first thing you might want to do is this solution, because that is the most intuitive one, I believe, if you know the concept. So I hope this helped. Every time there is something related to concept that you need to know to solve a problem, I'll first try to explain a little bit of the concept, the theory behind this problem, and then we'll apply this theory to the problem. See you in the next videos.